What does it take to build one of the most expensive construction projects in British history? A massive nuclear megaproject covering more than 2 million square meters, costing over $30 billion, and expected to power millions of homes for decades to come. Deep on Britain's coastline, thousands of workers are racing against time to construct a giant energy complex that could reshape the country's future. From colossal concrete structures and advanced nuclear reactors to engineering challenges never seen before, this project is pushing the limits of modern construction. Why is Britain spending so much on this single project? What makes it so controversial? And can this nuclear giant deliver the clean energy revolution it promises? In today's episode of Datascope, we're taking you inside Britain's $30 billion nuclear megaproject to uncover the incredible engineering, the staggering costs, and the future of energy itself. Let's get started. The UK has relied on coal and natural gas for electricity for decades, but increasing pressure to reduce carbon emissions has led to the phasing out of many thermal power plants. While renewable energy sources like wind and solar have grown, their instability poses challenges when conditions are unfavorable for generating power. This instability has prompted a search for a stable power source that also meets environmental standards. Nuclear energy emerged as a necessary solution, leading to the proposal of Hinkley Point C as part of a strategy to enhance energy security and achieve net zero emissions. However, this pursuit comes with significant risks related to construction costs and the complexities of the technology involved. I am witnessing the construction of Hinkley Point C on the southern shore of the Bristol Channel, which is the largest construction project in Europe, covering nearly 2 million square meters. Designed around the advanced EPR reactor, the plant features a multi-layered safety structure ensuring that it is built to never fail. The coastal area of Somerset posed challenges due to weak soil conditions and tidal movements, necessitating a large-scale ground improvement program with 29 kilometers of steel piles. At the peak of construction, over 2,000 workers transformed the site into an industrial zone, with the establishment of concrete batching plants and dedicated transport routes. This project highlights the extensive preparation required to support the construction of such a massive nuclear facility in a difficult environment. Once I completed the ground stabilization work, I moved on to pouring the plant's foundation structures, which needed to meet strict precision requirements to avoid affecting sensitive nuclear equipment installations. The reactor area required a remarkably thick and stable foundation to serve as the heart of the power station. To ensure quality, I produced the concrete on site while carefully controlling temperature, moisture levels, and material composition. During peak construction periods, I poured thousands of cubic meters of concrete continuously, creating structures capable of supporting enormous loads for decades. Additionally, I oversaw the construction of a vital seawater cooling tunnel system, which involved excavating tunnels several kilometers beneath the seabed, drawing seawater into the station for heat exchange with the reactor cooling systems. I installed large vertical shafts with extreme precision to connect the power station to the underground tunnel network. This part of the project was particularly challenging due to high-pressure conditions and complicated marine geology, requiring near-absolute positioning accuracy. Once finished, the system created a large-scale cooling water circulation route that helps the plant maintain stable operating temperatures for its reactors over decades. The reactor zone is the most complex and critical area of the nuclear power plant, where the strictest safety standards, structural requirements, and quality control procedures are enforced. The construction process begins with building the containment building, a massive protective structure that encases the entire reactor. I build the containment structure layer by layer and segment by segment, rather than using a single concrete pour. Large-scale formwork systems are installed first, followed by concrete being poured floor by floor. Alongside the outer concrete structure, I install an internal airtight steel shell, known as the steel liner, piece by piece to prevent any radioactive leakage. Each steel plate is welded with high precision and inspected thoroughly before final approval, ensuring stability and airtight performance under nuclear safety standards. Once the containment structure is completed, I proceed to the next major phase, which involves installing the nuclear equipment. I followed an extremely strict sequence for the process. I positioned the reactor pressure vessel, the largest and most critical component, at the center of the reactor building. Weighing several hundred tons, this component required heavy lift crane systems and precise alignment operations. After securing the vessel in place, I installed the rest of the reactor systems around it. I then proceeded with the installation of the steam generators, primary circuit piping system, and heat exchange equipment, which together transfer energy from the reactor core to the power plant. Every connection had to meet absolute sealing standards to withstand extreme pressure and temperature conditions during operation. Hundreds of kilometers of piping were installed, welded, and inspected using non-destructive testing methods to ensure no defects remained. The reactor produces steam that drives massive turbines, converting thermal energy into electrical power for millions of households. The entire electrical system was eventually connected to the national grid, marking Hinkley Point C as an active component of the country's energy infrastructure. Additionally, supporting facilities were constructed, including spent fuel storage buildings designed for complete radioactive isolation in accordance with strict nuclear safety standards. The main control room at the plant is where engineers monitor the station's operating status through thousands of real-time data signals. This room acts as the brain of the complex, overseeing reactor temperature, cooling systems, and electrical network performance. For Hinkley Point C to operate for many years, infrastructure for the workforce must be developed alongside the technical systems. A large staff support area was constructed next to the site to accommodate thousands of engineers and workers on continuous shifts. This area features accommodation, dining facilities, medical services, and fire response units, supporting tens of thousands of active workers during peak construction periods. To sustain the pace of construction at Hinkley Point C, I connected the entire project area through a complex logistics network, ensuring materials, equipment, and workforce resources were consistently available. Hinkley Point C is the first nuclear power plant built in the UK in several decades and is anticipated to lead to a new generation of energy infrastructure. However, I faced significant controversy and opposition from various organizations from the project's inception. Concerns regarding cost, safety, and long-term effectiveness have continually impacted the progress of the project. As construction costs have escalated, I now expect it to become one of the most expensive nuclear power plants ever constructed. Originally scheduled for completion in 2027 at an estimated cost of £26 billion, the plant is now unlikely to begin operation before 2030, with revised costs projected between £31 billion and £34 billion. The chief executive of Hinkley Point C communicated to workers that the COVID-19 pandemic alone caused a delay of about 15 months. The construction process has significantly impacted the coastal ecosystem of Somerset. Activities such as constructing seawalls, excavating tunnels beneath the seabed, and transporting massive amounts of materials have altered the natural landscape and affected marine species and habitats. The plant's cooling system uses a large volume of seawater daily, and if the water discharged back into the sea at a higher temperature is not carefully controlled, it could adversely affect the marine ecosystem. Engineers have put various measures in place to mitigate environmental impacts, such as filtration systems to protect marine life and regulating discharge water temperatures. Once operational, Hinkley Point C will supply significant low-carbon electricity, aiding in the reduction of fossil fuel reliance. To minimize future environmental effects, society needs to accept present trade-offs. This site exemplifies the transformation of the energy system in the 21st century, evolving from a quiet coastline to a complex infrastructure project. Despite concerns regarding costs and risks, Hinkley Point C is vital to the UK's strategy for energy security and carbon emission reduction for the future. As Britain continues building this massive $30 billion nuclear megaproject, its success could shape the future of energy not only for the United Kingdom, but for the entire world. From groundbreaking engineering and giant construction efforts to the promise of cleaner and more reliable power, this project stands as one of the most ambitious infrastructure undertakings of the 21st century. What do you think? Will this nuclear megaproject transform Britain's energy future, or are the costs and challenges simply too great? Let us know your thoughts in the comments below.
Once completed, it will not only provide electricity to millions of households, but also raise a larger question for the future. Will nuclear power continue to remain an essential part of the modern global energy system? What do you think about this choice? Share your thoughts in the comments below. And if you would like to explore more mega projects like this one, don't forget to like the video